I want you to try something for me. Just for a second, hold out your hand.
And really look at it.
Yeah, look at it. Wiggle your fingers. Now look past your hand at the wall or the window, whatever is in front of you. It feels solid, right? You perceive depth. You feel the weight of your body in the chair. You are absolutely certain that you're inhabiting a three-dimensional world.
I mean, it's the most fundamental assumption we make. It's the stage where our entire lives play out. Up, down, left, right, forward, back.
Exactly. But here's the thing that's been kind of driving me crazy since I started reading through the stack for today's deep dive. What if that solidity is a lie? Or maybe not a lie, but...
User interface.
Right. What if the three-dimensional universe we see is actually just a projection? Like a hologram generated from a flat, two-dimensional surface at the edge of the cosmos? And what if the reason we think we feel gravity isn't because the Earth is pulling us, but because we're sliding along a curved geometric sheet?
You're really jumping right into the deep end today.
I have to. I mean, this material is absolutely wild. We're looking at a huge stack of sources today that cover general relativity, the black hole information paradox, the holographic principle, and a really dense but totally fascinating breakdown of dimensions from the Academy of Sciences in Murcia.
It is a heavy stack, for sure. But you're right to start with that feeling of reality. Because the story of modern physics, from Einstein to string theory, is basically the story of realizing that our common sense is wrong. The universe is not what it looks like.
So the mission today is that we need to connect all these dots. We need to go from gravity's geometry all the way to the world is a hologram. And frankly, I need you to help me not lose my mind in the process, because some of this stuff feels like it completely breaks the rules of logic.
Well, it breaks the rules of Newtonian logic,
Mm.
but it follows a much deeper logic. To understand the hologram idea, we really have to start where the trouble began. We have to start with gravity.
Okay, gravity, the thing that makes me drop my phone on my face when I'm scrolling in bed. Isaac Newton said, it's a force, right? Mass attracts mass. The Earth pulls the phone.
Yeah, and that was the gold standard for centuries. I mean, it works for building bridges, it works for firing cannonballs. But then in 1915, Albert Einstein published General Relativity and basically said, Newton, you're wrong. There's no force. There's no invisible tether pulling your phone.
This is the part I always kind of struggle to visualize. If nothing is pulling the phone, why does it fall?
Because the phone is trying to move in a straight line, but the straight line itself has been bent. Einstein's big insight was that gravity is actually the curvature of space-time.
Space-time.
Right. Think of space and time not as an empty void, but as a fabric. A trampoline is the classic analogy, though. It's a bit limited. You put a bowling ball, which is the sun, in the middle of the trampoline.
Yeah.
The fabric sags.
Okay.
Now you roll a marble, the earth past it, the marble curves around the bowling ball. Not because the ball grabbed it, but because the surface it's rolling on is curved. As the physicist John Archibald Wheeler put it, space-time tells matter how to move, and matter tells space-time how to curve.
I've seen that diagram in textbooks, but here is where I get stuck. That's 2D. We live in 3D. How does 3D space curve?
It's incredibly hard for our brains to picture. We aren't wired for it at all. There's a famous thought experiment Einstein used that helps lock it in. It's called the equivalence principle.
Well, the elevator scene. I love this in the notes.
Yeah, it was Einstein's happiest thought. Imagine you wake up in a windowless room. You feel heavy. Your feet are pressed against the floor. If you drop your keys, they hit the floor. You would assume naturally that you're on Earth feeling gravity.
Sure, I drop something, it falls. Gravity.
But Einstein realized that you would feel the exact same sensation if you were actually in a rocket ship deep in empty space, accelerating upwards at 9.8 meters per second squared. The floor of the rocket would be pushing up into your feet.
So the keys aren't falling.
Exactly. The keys aren't falling, the floor is rushing up to meet them.
And there is literally no test I could do inside that room to tell the difference.
None. Physically, they are identical. This implies that falling under gravity isn't being pulled. It's actually what we call inertial motion. When you're in free fall, like an astronaut orbiting the Earth, you feel weightless because you're just following the natural curve of space. The geodesic.
Wait, so the only reason I feel weight right now in my chair is because the chair is preventing me from following that curve.
You got it. The ground is constantly accelerating you upwards, away from the straightest path through space-time.
Okay, that is trippy. But let's play devil's advocate here. It's a beautiful theory. It sounds poetic. But is it real? Or is it just fancy math on a chalkboard?
It is very real. And the proof is actually one of the most dramatic stories in science history. We have to go back to 1919.
The Eclipse Expedition.
Right. Context matters here. World War I had just ended. Europe was a total mess. You have a German scientist, Einstein, proposing a theory that overthrows Newton, the absolute pride of British science. And you have a British astronomer, Arthur Eddington, who decides to test it.
The stakes must have been incredibly high.
Enormous. Einstein claimed that because gravity curves space, it should also bend light. If you look at a star positioned right next to the sun, its light should curve around the sun, making the star appear in the wrong place.
But you can't see stars next to the sun. It's way too bright.
Unless you have a total solar eclipse. So Eddington hauled all his equipment to the island of Principe off the coast of Africa. He had to deal with clouds, rain, mosquitoes, equipment failure. If the weather hadn't cleared at the very last minute, we might not have accepted relativity for another decade.
And the result? Did the stars move?
They shifted. Not by much, just about the width of a human hair seen from 50 feet away. But they shifted exactly as much as Einstein predicted. Space acts like a lens. It was front-page news worldwide.
That's amazing. And the sources also talked about the orbit of Mercury, right?
Yes, the anomalous perihelion advance. Basically, Mercury's orbit rotates slightly in a way Newton's math couldn't explain. Einstein's curved space-time fixed the math perfectly.
And today, we don't even need an eclipse or a planet to prove it. The notes mentioned GPS. I didn't realize my map app was relying on this stuff.
Oh, absolutely. If we turned off the relativistic corrections, your GPS would drift by about 10 kilometers every single day.
10 kilometers. So I'd be in the next town over just trying to find a coffee shop.
Easily. The satellites are high up, far from Earth's mass.
Yeah.
Gravity is weaker there. And general relativity says that where gravity is weaker, time actually moves faster.
Wait time moves faster?
Yes. The clocks on the satellites literally tick faster than the clocks on your phone down here on Earth. Engineers have to program the satellites to artificially slow down their clocks to match ours. They are literally correcting for the curvature of time.
Man, that is wild. And we even felt those ripples in space recently, right? The LIGO detection.
Gravitational waves, exactly. In 2016, the LIGO Observatory detected literal ripples in the fabric of space-time from two black holes colliding over 1 billion light years away.
Okay, so that's the proof right there. Gravity is geometry. We're living in a warped reality. But this brings us to the villain of the story. Or maybe the plot twist. Black holes.
The exact place where the geometry breaks down.
So we know black holes are these gravity pits where nothing escapes, but in the source material, there is this massive conflict called the information paradox.
Yeah.
What is the actual problem there? Why were physicists fighting about this?
It comes down to stuff. In physics, we believe that information is never lost. If I burn a book, the information in that book isn't technically gone. It's scrambled into ash and smoke and heat.
Yeah.
If you had a supercomputer, you could theoretically reverse the process and read the book again.
Okay, so nature basically doesn't have a delete button.
Exactly. But then you have a black hole. For a long time, the prevailing theory, which was Stephen Hawking's early theory, was that black holes were just smooth, featureless pits with zero entropy. If you throw a messy library into a clean black hole, it's just gone.
And the black hole eventually evaporates, right? So the book is permanently deleted.
Right. And that totally violates the second law of thermodynamics and the laws of quantum mechanics. It's a paradox. But then a graduate student named Jacob Bekenstein came along and suggested something that seemed crazy at the time. He said, wait, the black hole must have entropy.
Entropy usually means disorder, right? Like a messy bedroom has high entropy.
Right. But in this context, think of entropy as hidden information, the amount of data needed to describe the mess. Bekenstein realized that if you throw a book into a black hole, the black hole's event horizon, its surface area, gets a little bit bigger.
Okay, bigger belly. That makes sense.
But here's the weird part, the twist that changes absolutely everything. Usually if you want to store more stuff, you need more volume. If you want to store more water, you need a bigger bucket. Capacity scales with volume.
Right, in normal 3D space.
Right. But Bekenstein found that for a black hole, the capacity to store information doesn't scale with the volume inside. It scales with the surface area of the outside.
Wait, pause. You're saying the amount of stuff a black hole can hold depends on the skin, not the inside.
Precisely. Imagine a library. You'd think the number of books you can fit depends on the size of the room. But Bekenstein's math says no. The number of books you can fit depends on how much wallpaper you can put on the walls.
That completely breaks my brain. Why?
It suggests that when something falls into a black hole, the information about that object isn't lost inside. Instead, it gets smeared out and encoded on the two-dimensional surface of the event horizon. It's like a soup can.
A soup can?
Yeah, think about a can of soup. The reality, the flavor, the noodles, the chemistry is the 3D stuff inside the can. But if you look at the label on the outside, it contains data describing the soup. Bekenstein and later physicists like Susskind and Hooft realized that for a black hole, the label is all there is.
So the 3D interior might just be a projection of the 2D surface data.
Exactly.
And this is where we finally get to the holographic principle. Because they didn't just stop at black holes, did they?
No, they took the leap. If the most extreme object in the universe, a black hole, stores its reality on its surface, maybe everything does. Maybe the entire universe is just a soup can.
So when we say hologram, we don't mean R2-D2 projecting a blue ghost. We mean what exactly?
We mean that the physics of our 3D world, the gravity, the stars, might be mathematically equivalent to a set of quantum laws operating on a distant 2D boundary. The 3D world is just an image of reality coded on that surface.
Is there any solid proof for this? Or is it just a really cool idea?
There is a very strong mathematical proof, but it's dense. It's called the ED-SEFT correspondence.
Which sounds like a terrible Wi-Fi password.
It really does.
Yeah.
But let me use an analogy that might land better than the acronym. Do you play video games?
I dabble, yeah.
Okay. Think about a game. When you're playing, you see a 3D world. You see depth. You see mountain shadows. You can walk forward and back. It feels like a 3D space.
Sure it does.
But where is that world actually located? It's located on a 2D silicon chip inside your console. It's just a flat stream of ones and zeros. The code is flat, but the experience is 3D. Juan Maldacena, the physicist who proposed ED-CFT, basically proved that you can have a universe that looks like the 3D video game, complete with gravity. And it is perfectly mathematically identical to a 2D code without gravity living on the edge of the screen.
That is insane. So gravity itself, the thing Einstein said was curved geometry, might just be the graphics engine of the simulation?
That is a brilliant way to put it.
Yeah.
Gravity might be emergent. It pops out of the interactions of the information on the boundary, just like a 3D image pops out of a flat hologram when you shine a laser on it.
This implies something else the sources mentioned too. Pixelation, like a limit on information density.
The Bekenstein bound, yes. If reality is information, and you could only fit so much information on a given surface area, then space can't be infinitely divisible. Eventually, if you zoom in far enough way past the atom, you hit the actual pixel size of the universe, the Planck length.
We're living in a pixelated projection. I feel like I need a drink. But before we wrap up, we have to talk about the other side of this coin. We've talked about removing a dimension going from 3D to 2D. But the Academy of Science's source also talks about adding dimensions.
Which brings us to a great mystery in physics. Why is gravity so weak?
Is it weak, though? It holds the moon in orbit.
Sure, but look at a fridge magnet. A tiny little magnet the size of a coin can pick up a paperclip. That magnet is fighting the gravitational pull of the entire Earth, and the tiny magnet wins.
I never actually thought about it that way. The whole planet is pulling down and one little magnet pulls up and wins. Gravity is a wimp.
Exactly. But why? This is where string theory and extra dimensions come in. The source breaks down dimensions really simply first. 1D is length like a line. 2D is width like a drawing on paper. 3D is depth like a box.
And Einstein added time as the fourth dimension.
Right, we move forward in time, but not backward. But back in the 1920s, a guy named Kaluza tried to unify gravity and electromagnetism in one equation. He found it didn't work in 4 dimensions. But if he added a 5th dimension, the math worked perfectly.
But we don't see a 5th dimension. I mean, I can't walk sideways out of reality.
No. So physicists had to explain where it was hiding. And they came up with the idea of compactification.
It's a straw analogy from the text.
Yes. Imagine you're looking at a garden hose lying across a football field. From way up in the stands, it looks like a line, one-dimensional, just length.
Right.
But if you're an ant crawling on the hose, you know there's a 2nd dimension. You can walk around the circular cross-section of the tube. The dimension is there. It's just curled up into a tiny circle.
So the idea is that our universe has the big 3 dimensions we see up, down, left, right, forward, back. But at every single point in space, there are tiny curled up dimensions.
Exactly. String theory suggests there could be 10, 11, maybe even 26 dimensions. But the extra ones are curled up so tightly smaller than an atom that we just don't experience them. But, and here's the connection, gravity might be able to.
So gravity's leaking into them.
That's the leading theory for why it's so weak. The other forces, like magnetism and the nuclear forces, might be stuck on our 3D membrane. But gravity might be leaking out into these extra dimensions, effectively diluting its strength.
So the magnet wins because gravity is distracted by wandering off into the 5th, 6th, and 7th dimensions.
It's highly possible, and we're actually testing this. The Large Hadron Collider, the big particle accelerator in Europe, is smashing particles together to see if we can find Kaluza-Klein particles or see if any energy just disappears
Disappears where?
into the bulk, into those higher dimensions. If we smash particles and the energy sums don't add up, it might be proof that some of the gravitational energy escaped into a dimension we can't see.
That is equal parts terrifying and amazing.
It's the absolute frontier of physics right now.
So let's try to pull this whole picture together because we've covered a ton of ground today. We started with the idea that the pull of gravity is actually an illusion caused by the curved geometry of spacetime.
Right.
Then we went to black holes and realized that the space inside a black hole doesn't matter nearly as much as the surface area outside. The soup can label holds all the data.
Which naturally gave us the holographic principle.
And finally, we learned that the 3D screen we are projected onto might be woven with tiny extra curled up dimensions that are secretly diluting gravity.
It really sounds like pure science fiction.
Yeah.
But mathematically, this is the best map of reality we currently have.
It changes how you look at the world. I mean, you go through your day worrying about traffic or what to eat for lunch, or we treat all these things as so solid and real. But if you zoom all the way out or zoom all the way in, it's all just information.
That's the key takeaway here. Wittgenstein said it best when he realized that volume is illusory. We are so obsessed with stuff, matter, volume. But the universe seems to care way more about the information describing the stuff. The geometry, the code on the boundary.
We are just the user interface.
And we are only just starting to figure out how to read the source code.
Well, I'm going to go stare at a garden hose and question my entire existence.
Sounds like a highly productive afternoon.
Thank you for walking us through the hologram today. And to everyone listening, keep looking at the label on the soup can. You never know what you might find hidden in the code. Catch you on the next deep dive.